In the last video, we talked about how every atom really wants to have 8, let me write that down, 8 electrons in its outermost shell. That this is kind of the most stable configuration that an electron could have. And given this fact that's been determined just by observing the world, really, we can start to figure out what's likely to happen in different groups of the periodic table. And a group of a periodic table is just a column of the periodic table, like this group right here. And actually, I'll start with this group because it's got a special name. This group right here is called the noble gases. And what's common when you go down a group in the periodic table? What's common about a column in the periodic table? In the last video, we saw that every element in a column has the same number of valence electrons, or it has the same number of electrons in its outermost shell. And we figured out what that was. This column right here, which we learned were the alkali metals, this has 1 electron in its outermost shell. And I made that one caveat that hydrogen isn't necessarily considered an alkali metal. One, it's usually not in metal form, and it doesn't want to give away electrons as much as other metals do. When people talk about metal-like characteristics of an element, they're really talking about how likely it is to give away electrons. But we'll talk about other characteristics of a metal, especially the way that we kind of perceive metals as being shiny and maybe they conduct electricity, and see how that plays out in the periodic table. But anyway, back to what I was talking about. This column right here, this is called the alkaline earth metals. So this is alkaline earth. Alkaline earth. These all have two atoms in its outermost shell. So remember, everyone wants to get to 8. If these guys wanted to get to 8 by adding electrons, they'd have a long way to go. This way, they would have to add 7 electrons. They would have to add 6 electrons, and who are they going to take it from? Because these guys don't want to give away their electrons. They're so close to getting to 8. So it's much easier when you're on the left-hand side of the periodic table to give away electrons. In fact, when you only have 1 to give away, that, especially in the case of elements other than hydrogen, when you only have 1 to give away, it really wants to do that. And because of that, these elements right here, they're very seldom found in their elemental state. When I say elemental state, it means there's nothing but lithium there, or there's nothing but sodium there, there's nothing but potassium there. They're very likely, if you find this, it's already reacted with something, probably with something on this side of the periodic table, because this wants to give away something really bad, this wants to take something really bad, so the reaction will probably happen. These are still reactive. The alkaline earth metals are still reactive, but not as reactive as the alkali metals. And that's because these guys are really close to getting to the stable, the magic 8 number. These guys are a little bit further away, so it takes a little bit more, I guess you could say, a little bit more of a push for them to give away 2. These guys only have to give away 1. And then we learned that this has 2 in its outermost shell, and then all of these elements, which are called the transition metals, as you add electrons, they're just backfilling the previous shell's d subshell, right? So their outermost shell still has 2. It still has those, if this is the 4th period, all of these elements' outermost shell has 4s2. And these elements are just backfilling their 3d suborbital, or their 3d subshell. So these are 2s. So these all have 2 outermost electrons. So all of these, like the alkaline earth metals, they need to lose 2 electrons in order to, quote unquote, be happy. And the way I think about this, and this is really just a way, and maybe it bears out in physical reality, is that these guys have kind of a deep bench of electrons. That if they are able to shed some of these valence electrons, so if I write iron has 2 valence electrons like that, even if they shed these electrons, they kind of have a reserve of electrons in the d subshell for the previous shell. So if it shed its 4s2 electrons, it still has all those 3d electrons that have a high energy state that can maybe kind of replace them. And I'll use everything in quotation marks because these are just ways for me to visualize things. And the reason why I make that point is because metals like to they're just very giving with their electrons. And these guys react. I mean, they just say, hey, take my electron. These guys say, take these two electrons. And these guys, they start to say, especially as you fill the d subcell, look, I got these two electrons, and not only do I have those two electrons, but I have more electrons where, well, almost where that came from. I have some in reserve in my d. And what happens in these transition metals, and it especially happens in the metals, so these are the metals right here, and these don't follow just a group, but this is the metals, this color right here, is that they have so many electrons to hand off. Not only do they have these extra there, but they filled their d sub shell that they can kind of, especially when they're in elemental form, and when I say elemental form, these means that you just have a big block of aluminum. Aluminum hasn't reacted with anything like oxygen. It's just a bunch of aluminum. Right? And when you have a bunch of aluminum, what happens is you have these metallic bonds where all of the aluminum atoms say, you know what, I have all these extra, I have definitely, well, in the case of aluminum, I have 3 electrons in my outermost shell, but I have all of these kind of backfilled electrons in my d suborbital. I'm just going to share them with the other aluminum atoms. So you create the sea of aluminum atoms, and they're attracted to each other, or you create the sea of aluminum electrons. So you have a bunch of electrons sitting in between the atoms, and since the atoms kind of donated these electrons, they're attracted to them, right? So the actual atoms, so this would be an aluminum plus, and maybe it would have donated 3 electrons. But this isn't, I'm not being exact here. I want to just give you the sense of how things work. And that's why metals conduct really well, because electricity is just a bunch of electrons moving. And in order to have electrons moving, you have to have surplus electrons laying around. So if elements right around this area are really good conductors. In fact, silver is the best conductor. Silver right here is the best conductor on the planet. And the reason why that's not used for our wiring and copper is because copper is easier to find than silver. But silver is the best conductor, and the way I think about it is that once you filled an orbital, that orbital becomes somewhat stable. So all of these guys have filled their d orbital, while these guys, their d orbital is not filled. So they just have a lot of surplus electrons that are really good for conduction. Now that's just an intuition. There's not, I haven't done the experiment to prove that, but it'll give you a sense of why things conduct and all of that. So these are the transition metals. These are actually considered the metals. But the reason why these are considered the transition metals is because they're filling the d block. But transition metals kind of sound like not as good as a metal. But when I think of metals, iron is kind of the first metal I always think of. I definitely think of silver and copper and gold as metals. So to call them transition metals is a little not fair. I don't really consider aluminum more of a metal than let's say iron is. But in chemistry classification world, aluminum is more of a metal. These elements right here, and I know I dropped off from kind of the group notion, but let me just actually write the valence electrons. So these all have 3 valence electrons, 4, 5, 6, 7. So these all have 3 electrons in its outermost shell. It still seems easier for them to give them away than to take them, but maybe now in certain cases, there could be, especially in the case of, let's say, boron, there could be a situation where it maybe could gain 5 electrons. Well, that seems hard to, that it's much easier to give away 3, and that's why a lot of the quote-unquote official metals show up in this category. And as you can see, as you go down the periodic table, you can kind of have metals that have more and more valence electrons. So for, this let's say lead, it's still a metal even though it has 4 valence electrons, and that's because the atom is so big that its radius is so large that the outermost shell is so far away from the nucleus that those electrons are easier to take off. So, for example, as you go down carbon, those electrons are very close to the nucleus. So they're very hard to take off. So carbon would probably more likely gain electrons from somebody else to get to 8. While these guys' valence electrons are so far away from the nucleus that they're more likely to kind of want to get rid of them to get to 8 and get back to an electron configuration of, let's say, xenon. And you go, and then these guys are the non-metals, right? They're likely to probably gain electrons in most reactions. And then this yellow category that I said was highly reactive, and especially highly reactive with the alkali metals over here. These are called halogens. And you've probably heard the word before, halogen lamps. That's no that's no I guess that's no mistake there to call them halogen lamps. That's not a random choice of words. And maybe I'll do a video on halogen lamps in the future. And then finally, we're at the noble gases. And what's interesting about the noble gases? Well, they have 8 electrons in their outermost shell, right? Except for helium. Helium has 2, right? Helium's electron configuration is 1s2. But all of these other guys, this guy's electron configuration is 1s2. This is neon. 1s2, 2s2, 2p6. So he has 8 electrons in his outermost shell. So he's happy. Argon, same thing. The outermost shell, the outermost shell will look like 3s2, 3p6. Krypton will have its outermost shell will be 3s2, 3p6. It'll also have some 3d electrons as it backfilled back here. But all of these have 8 in its outermost shell, so they're happy. They have no incentive to react. They're kind of like, hey, all of you other elements, just, you guys can do all that crazy reactions that you got to do, but we're happy and we don't want to give or take electrons. And because of that, these guys are highly, highly unreactive. Very, very unreactive. And back in the day when they used to make these kind of Zeppelins, these big blimps, the Hindenburg's a famous example. They used hydrogen, and obviously hydrogen is a pretty reactive substance. It's actually very combustible, and that's why it blows up very fast. And that's why now clowns or children's balloon manufacturers, they instead would prefer to use helium. Because helium is a noble gas, and it's very unreactive, and it's very unlikely to explode at a child's birthday party. But anyway, I think I'm done now with this video, and in the next video we'll talk a little bit more about trends across the periodic table.